So we took a very quick look at the kinds of evidences we have for interpreting past climate variabilities, and if we have a good measure of the perturbation forcing corresponding to those variabilities or change depending on the time scales, then we can put together a story of the response to the perturbation and the feedbacks. One of the key variabilities we have to worry about, of course, is the energy we are receiving from the sun. And solar activity has varied on all sorts of time scales. In fact, when the Earth system, when the solar system formed, solar physics tells us that sun was 30% less bright, so the energy coming in was 30% less. Then you get into various needs to explain how water would have remained in liquid form on Earth if the sun was so faint. So that's called the young sun paradox. We need liquid water because by all measures life would have happened in the liquid water, plus there is evidence of liquid water from the beginning. There is a whole other debate on where the water would have come from, but now latest research shows that the material with which the solar system started already had plenty of water in it, so the Earth got formed with material that had plenty of water in them, okay, called chondrites and so on and so forth. The other more well-known solar activities are so-called sunspots, which has an 11-year time scale, but also has these kinds of episodic minimum of solar activity in terms of sunspots. Basically, these are magnetic storms that twist and create black spots on the sun, but around the black spot a very bright plage gets formed. So actually, as number of sunspots increases, the radiative output increases. So minimum, solar minimum, like here Oort minimum, Wolf, Sporer and Maunder minima, and the Maurer maxima actually correspond to low solar radiation and high solar radiation. In fact, this created a lot of buzz by some people saying global warming can be explained by solar activity. As we will see later on, that this actually is not true. We have a very good idea of what the resulting perturbation is, and this is measured in the past, going back to here a millennium or half a millennium and so on, by using chemical isotopic signatures left behind. For example, C14, which is a carbon isotope, has obviously instead of 6 protons and 6 neutrons, has 8 protons and 6 protons and 8 neutrons. Protons define the element, atomic number, so you can have more neutrons, and it's unstable. How is it created? You think about something else that has a mass of 14, that's nitrogen. It has 7 protons and 7 neutrons. The galactic cosmic rays that are bombarding the atmosphere all the time can knock out a proton from a nitrogen which is so abundant and convert it into a neutron. So instead of N7 plus 7, it becomes carbon C plus 8. And then immediately this C14 begins to decay, and we already saw the decay time of some 8,750 years or so. Please check. So whenever photosynthesis happens, trees form and so on, they are taking a certain amount of C14, that's the background concentration in the atmosphere, and if that organic matter is hidden away, then it begins to decay. So you can take old organic matter like fossil fuels, look at the depletion of C14 and say how old it is based on the half-time of the half-life. So obviously you can only go back to about 50,000 years with this, but that can be used in terms of the production of C14 and related to solar activity as well. There are other isotopes like beryllium-10, and there are recorded sunspot numbers as well in some Chinese records, and so on. So we will see other examples of how we actually measure perturbations. Okay, so this is about 5 minutes long, so let me go another minute here. We don't always have enough data on perturbation and enough data for interpreting the responses to the perturbation. So we rely a lot on models. Models are incredibly useful tools. Despite all the problems people keep highlighting, the amazing thing is you put together the atmospheric model, the ocean model, the land model, vegetation model. We'll see a little bit more later. We saw a little bit in the first chapter. You give it the energy coming from the sun, and they can produce everything: weather, climate, monsoons, El Nino, the intertropical convergence zone, PDO, and so on. There are some issues. They don't match everything perfectly, so there are reasons for it in terms of not knowing processes in some cases, like cloud formation and convection, for example, or not representing all the details like the dynamic vegetation or land ice sheets and so on and so forth. Okay, so this is the temporal coverage or model capability, 100 elapsed days per year. So you can go from 10 to the minus 2 days to 1 day to 100 days, so days, years, decades, millennia, and epochs. And the computer models take a lot of time and a lot of processors, supercomputers, and so on. So it's not possible to run them for a very long time. If you want to run them for a very long time, you have to sacrifice the representation, let's say, of how many grids or how the sphere is split into how many boxes, okay, and so on. So you can see that the resolution varies from over 500 kilometers, which are models like this, which can be run for millennia, and down to 100 kilometers like models like HADGEM3, which can only be run at decades and maybe multiple decades. All the IPCC models, for example, are run for a couple of centuries, and that requires enormous amount of computing power. So to look at some of the processes, here we have observational timescales, remote sensing, meteorology and climate records, forest inventories, ocean carbon, ocean temperatures, and so on, tree ring records, lake and marine sediment records, ice core records, and so on. So we have to intelligently combine the evidence we have from observations, the perturbation knowledge we have from observations, the processes we can derive from observations, and use the models to first validate that the models can do the observed processes, and then understand the feedback processes, which are not at all easy to derive directly from observations. So that's how you would combine the two to produce more intricate, more detailed process understanding, so that you increase your predictive understanding, and projection is made possible because of that predictive understanding. Okay, so I will go into more details on the scales of the processes that are required to be resolved, especially because we are not talking about just physical climate, right? This is the main goal of this course, is to think about biogeochemistry, ecosystem, including human agency. So we must understand the feedbacks of the biogeochemistry and ecosystems in the past, when human beings were not big players in the perturbing the system, but also into the future, how human activity is perturbing the Earth system and the climate system. So we'll look at the scales that are typically resolved and the processes associated with them, and the compromises that are needed to accomplish some of these simulations to understand perturbations and responses.